Welcome back. Today we are going to talk about the machine haptics. We are starting a new second phase of our course in machine haptics. So far we have been looking at the human haptics part of it. Whatever we have learned in human haptics, we are going to use it to simulate the haptics part of it. Okay. So, before we see the human haptics, again if you look at just to summarize what we have been learning is specifically about the human hand, is that human hand has large number of degrees of freedom. You are talking about now 23 or 24 degrees of freedom, and extreme sensitivity of the cutaneous receptors, specifically in the finger pad the cutaneous receptors are extremely sensitive. And when we design machine haptics, we have to achieve this kind of cutaneous receptor sensitivities. The joints, if you look at it, the joints are sensors and actuators without frictions. So, very less frictions. Okay. So, in our machine haptics also we have to achieve this kind of frictionless sensors and actuators. And the control systems, when we look at it, it is highly adaptive control systems. Okay. We are going to see how what kind of control systems we are going to develop for haptic devices, and also how to make it now adaptive control system for these haptic devices. Okay. So, if you look at the way we handle objects, it can be divided into three different grasp type of the grasps. One is the contact grasp, where we can use only one finger and or now thumb alone, or now hands for the purpose of contacting objects. Okay. Hand in a combing condition, these are the different contact grasps. Precision grasps, where we emphasis on the control. Okay. So, minimum we use 2 fingers for precision grasps, or 3 fingers for equally distributed precision grasps, or 5 fingers, or equally distributed 5 different fingers on. And then power grasp, where we emphasize on the force generated in the human hands. 2 fingers can generate some force, 3 fingers can generate more force, 4 fingers or the entire hands can be used. Now, when we generate, how are we going to enable this in the machine haptics is what we are going to see. It is a very complex task, and it took, the research has started about now 1960s. It is a very 60 years old topic. How the research evolved is also we are going to see in the human machine haptics. Okay. So, this cycle, if you look at it, this is what we had understood in the earlier class, where we focused on the human haptics, and the same thing is what replicated in the machine haptics. In the human haptics, essentially if you look at only the contact purpose of the grasping, when an user is touching an object, let us say it is a real object, the contact forces are sensed by the mechanoreceptors, and the mechanoreceptors are conveyed to the brain, where we perceive and we react to the perception using the motor commands, and the motor commands are given to the muscles. The muscle generate forces and motions, and that is how the hand moves and perceives objects. The same thing we can convert it into machine haptics, where the motions, suppose if the human finger is attached to the end effector of a robotic device. This robotic device movement can be sensed by the sensors, movement sensors, and that is going to give the position information to the computer. The computer can generate torque, and then actuators can apply force to the end effector, and that will be the end effector will be resisting the movement of the user. That is how we can feel the forces. This is one way of machine haptics. This is called the kinesthetic devices, because we are using the only the kinesthetic sensors over here, the joint sensors, where the position information is inferred, and that is what is controlled, that is called the kinesthetic device. Another classes of haptic devices is the tactile device, where there will be an array of pins. It will move up and down depending upon the profile of the surface it can generate, that is a tactile devices. These two different classes of devices are in machine haptics. We will focus on kinesthetic devices in today's class. Later on we will focus on the tactile devices. So, we are all aware of computer mouse. With a very short introduction to what a haptic device is, can we differentiate between a computer mouse and a haptic device? So, we have the computer over here, let us say this is a computer, we have the user over here, let us say this is a user, and we have the computer mouse over here. So, the user see the computer, and he uses the mouse, and the mouse interacts with the computer. Probably the user also can view back the visual feedback given to the user. That is a very simple model of the mouse. What will happen if it is a haptic device? We are talking about the kinesthetic device. Suppose if we have this computer again, and if we have the user again user can interact with the computer, and just like a mouse, the haptic device also is going to be attached to the fingertip of the user, and this is going to be connected to the computer. So, it is almost like a computer mouse. What could be the difference? The difference is that the haptic device not only sensing, this is sensing the position of the user, right. So, it not only senses the position, but also feedbacks the user, force feedback to the user. So, this simultaneous sensing as well as actuation is the very important distinction between a haptic device and other devices, other sensing devices. Think about your cell phone. Cell phone again, it is a touch screen, we call it as, but again the touch screen, it is acting like only the sensing the position. It is not going to give you touch feedback at all. So, as Apple calls their iPhone devices as a haptic device, that is actually technically wrong. It is not going to give you force feedback depending upon the position. It is giving a general feedback, it is simple vibration. It is like touching a button or whatever. That vibration is a very limited vibrotactile feedback. It is not a haptic feedback. Haptic feedback, we are going to see in detail that it has to give a force feedback. Okay, vibrotactile feedback is not the force feedback. You are going to see the differences over here. So, the simultaneous sensing as well as the force feedback is one of the important characteristic of a haptic device. Now, let us look at the model of a user in a haptic system. Okay. So, essentially let us say we have the device, kinesthetic device, and here we have the user. The user moves the finger and therefore is giving a position out to the device, position and is input to the kinesthetic device, and the kinesthetic device generates a force output, and that is going to be given to the user. Okay. That is the kinesthetic haptic device. If you model the user, so the force output is coming from the kinesthetic device, and this force output is changing, stretching the skin, tactile let us say tactile system as well as the kinesthetic system. So, SPO is the, let us say this is a spontaneous reaction, spontaneous reaction of the user for the force which is coming from the device, and he is also perceiving because of the forces, he is perceiving the forces. Let us say that perception of the forces is k, and that is given to the CNS perception system, and there is a reaction to the perception. Okay. And the reaction is converted into action to the muscle and joints, and that reaction is going to be, let us say, induced reaction. The spontaneous reaction is the unintended reaction, voluntary reaction. This is the induced reaction, conscious reaction. Together they are all summed up. So, we get a final V out, and this final V out we can convert that into now X out, position output, and that is what given to the user. This is one simple model of user using the kinesthetic device. Okay. The same thing if you look at for the tactile device, this is for the tactile device, this for the kinesthetic device. So, in the tactile device what he is doing is we are going to keep the finger on the array of pins. So, you are going to move it, you are going to let us say apply force onto the tactile devices, and the tactile devices are going to move the pins up and down depending upon the configuration you want to see. Let us say a braille system, okay, that is a typical tactile system, right. So, in this case how are we going to model the user? Again the position output is coming from the tactile devices, and this tactile device, let us say, that is converted into now V out, velocity out, using the differentiation, and that differentiation is again and sensed by the skin, and so here the user is perceiving the user is has a perception of the tactile device, and the perception is converted into reaction. This again an induced reaction, right, induced reaction, voluntary reaction, and then voluntary reaction is moving the fingertip, and that fingertip movement is summed up, and then the resultant velocity is what given to the skin, and then that is what the user is actually perceiving. This perception is again, that is a whole cycle of it. Okay. So, that is a tactile device is model of user. Okay. what we will be focusing is only on the kinesthetic device. Now, this model of the user, we can consider that as all those abstracts can be converted into a transfer function looking from the system's point of view. We can make it as a transfer function of each of the small blocks, and this transfer functions if we can find out, and we can have a much better control of the devices, and that is one of the important and stages of machine haptics that is also involved in the human haptics. How are we going to evaluate each of these transfer functions? Okay, that is it is still an active research, and people are still struggling to find out how to find out the transfer functions or of each of the blocks. Okay. This is for kinesthetic system, and then next slide is for tactile systems. We will see in details in the coming classes, but I hope you see how we are approaching the machine haptics. All right. So, now we have an idea about how we want to go about it, but one of the major important and challenge in the human haptics is the actuator. Okay. So, any mechanical device will have its own intrinsic properties. So, it will have friction, it will have mass, compliance, viscosity, but what we are looking for is that a device, an actuator without friction, an actuator without mass, an actuator which can deliver a lot of very high range of compliances or very less right amount of viscosity. Okay. So, these are all ideal conditions. With ideal conditions only we can design a better haptic device. So, visual interfaces exploit the limitations of the visual apparatus. You are watching this display, the visual display which is flickering at 30 hertz. Those of you who are watching the video, it may be flickering 60 hertz, and that 60 hertz is decided exploiting the limitations of the visual apparatus. Similarly, can we find out what is the limitation from the our haptic systems, which we can also exploit in the design of the haptic systems. So, in the human haptics we studied that we need at least 1000 hertz in order to make the user not feel the vibration. That could be equivalent to 30 hertz in the visual systems, whereas in the haptic systems we are going to talk about the 1000 hertz update rate. Okay. Human haptic systems has also limitations, and that limitations, lot of limitations. One of the limitations is that until 1000 hertz we will be feeling the vibrations just like the visual systems. So, we need to understand the biomechanics, sensory motor systems leading to the perceptions. That is what we have done in the human haptic systems. We will use a lot of those numbers from the human haptic systems. These are all some of the already available haptic devices. One of the first haptic devices which came into market sometime in 1990s is this force feedback joysticks. Okay. I think I have a very nice personal anecdote of working with the inventor of the first force feedback joystick. It was a lady, okay, Beth Marcus. She is alumnus of MIT. She started this company, very small company. Okay, she made this force feedback joystick and then sold it to Microsoft for a huge money. There was a time the .com bubble is yet to come. Okay, she made a lot of money, and then she started making more companies, and then invested in a lot of .com companies, and then finally it was she lost almost all the money back. Okay. So, I had a chance to work on this first force feedback joystick when Microsoft was sued by one of the another companies is for designing for the patent on this first force feedback joysticks. So, we had to make some demonstrations and to make it as a legal case and then produce it in the court to win the case. Okay. That was very, so that is one of the first force feedback joysticks. And then came force feedback mouse. Have you seen this? So, the ordinary computer mouse will not resist your movements, but suppose if the position of the mouse can be restricted in a 2D. Okay. So, that using a 2D haptic device, that is the computer mouse. Okay. So, there are exoskeletons, again one of the earlier ones. Major challenge with the exoskeleton is that you can see that the amount of linkages and then actuators in the human hand is enormous. What we want is all these devices should be as light as possible. In fact, zero mass is what our ideal requirement is. That is not at all possible. So, you have to, the user has to carry all these masses and it is going to generate a small force on your finger that is going to be killing the feeling of the immersion, the feeling of the purpose of the haptic devices. Similarly, the cyber glove also. So, we are going to review all this machine haptic interfaces in a detail later. These are the one of the few reason exoskeletons. One of the earlier 2D haptic device is called the pantograph. Sorry. So, this pantograph has a parallel architecture. The user is holding over here and he moves in 2 dimension, and there are 2 actuators for one arm, one actuator for one arm, another actuator for another arm. So, there are 2 actuators which is controlling the position of the x and y axis. This is from Canadian Academic Institute, which is very well known, called the pantographs. We are going to see in detail. iDrive for navigation is one of the latest haptic device, but it is 1 degree of freedom. I don't know how many of you have heard about BMW in their latest versions has this device. It is called the iDrive. Okay. So, just hold the knob over here. Okay. While driving, essentially in the Europe, if you look at it, the roads are very fine. You can drive the car at 200 kilometers per hour or whatever it is, right. So, when you are traveling at 200 or 300 kilometers per hour, a very small mistake you do, if you take off your eyes from the road you are in great danger. So, we need lot of interfaces to help the user or the driver to manipulate objects in the car without taking the eyes off from the road. So, there are AC switches, there are fan and radio, there are so many controls in the dashboard of the car, okay, but the user has to access it, but he can't take the eyes off the road. Okay. One way is using this iDrive. You just reach it and then navigate all the controls in the dashboard using only one point contact. Okay. So, it has a 1 degree of freedom. Using this simple haptic feedback, you can control many of the things. Okay. So, even though it was considered as a major technology, BMW had this device in most of the cars. At the latest edition of the BMW, this is not there. Okay. So, it may be a good exercise for you to find out why BMW did not include the iDrive in the latest cars. I would like you to think about it. The market leader in the haptic devices is called the Sensible Phantom. Okay. So, Sensible Phantom, you hold this stylus like a pen and then move this manipulator and this device is going to give you a resistance. This is this device is a startup company from MIT and still it is the leader in the haptic devices. Each one is this is a 3 degree of freedom force feedback, but its a sensing is 6 degree of freedom. Okay. Sensing is different from the actuation back. Okay. So, sensing can be 6 degree of freedom, but force feedback is only 3 degree of freedom. These are all the higher end. Here it is going to be workspace is going to be more force it can generate. Okay. This is even higher version and this is even higher version, and there is one version this is 1.5, there is one version now 6.0 also is there. Okay. So, 6.0 is going to be as tall as a human being. Okay. And we can move our hands in a large workspace. Okay. That cost is very high. Okay. We are going to study in detail how this Phantom is working. Okay. One of the cheapest devices in the market is called the Novint Falcon. Again, is one of the inventors of this Novint Falcon is from MIT. It cost just $200 or 200 euros. As its now its resolution is very poor, the force feedback also is very poor, and workspace also is very poor. It is a very small workspace. Okay. And it is again a trade-off position sensing as well as the force feedback, both the things. Okay. Again we are going to see how to make a very simple haptic device as a part of this course. Okay. So, recently there are new players apart from the Sensible Phantom. They are called force dimensions, which can give you more forces, and there are 3-DOF versions and there are 6-DOF versions, and again we are going to see different architectures of the haptic devices. These are all parallel architectures, where the Phantom one which you have seen earlier, that is all the serial architectures. We are going to see what are the different kinematic chains used to develop haptic devices. Most of the things this devices, all this any haptic devices can be considered as advanced robotic devices. Okay. We are also going to see what is the difference between the robotic device and a haptic device. Okay. So, all this concept the robotic device students and can will find out a lot of commonality between the haptic device design and the robotic devices, and you will find and what more is needed in order to design a haptic device. It is much more challenging than just developing a haptic robotic device. Okay. These are the specifications of the delta 3-DOF. Again the maximum force it can give you is 20 Newton. 20 Newton is about how much 2 kg. If you can hold 2 kg weight, that much force it can give you in each of those degree of freedoms. They have a recent version of Omega again, and the difference is that 6 degree of freedom, and they have 12 Newton, which is much lesser, and it is using the delta based kinematics. Those of the robotic students will understand it is a parallel, specifically delta structure, kinematic structure. Okay. We are going to see different type of the haptic devices, as where one device is called the haptic masters. Again, is very well known. It is a very distinct, different from all the existing haptic devices. It is the isometric device. It is also called the admittance device. We are going to see, when we are talking about the different control systems necessary for the haptic devices, we are going to use either impedance devices or admittance devices. Most of the haptic devices available in the market use the impedance control, whereas haptic master is using the admittance control. We are going to see different isometric, this is impedance as well as the admittance in the coming classes. Okay. This is our own haptic device which we have designed specifically for the laparoscopy surgical simulator. This is this is for one hand, this for the another hand. Each hand is a 5 degree of freedom, sensing as well as the force feedback, both sensing as well as the force feedback. Sorry, the workspace requirement is as dictated by the laparoscopic surgeons. Whatever they wanted, that has been incorporated over here. If such a device has to be bought, imported from other countries, it cost about 2 crore, whereas in IIT Madras the whole device has been fabricated within the campus, okay, and it cost much less than 5 lakhs. Okay, that is a innovation we could bring it. So, that device has been put in inside the small box over here, and the final device what the doctors will use is going to be something like this. Okay. This is one of our research scholars using this device. Okay. All the commercially existing devices can be compared in 2 different axes. Suppose if we compare in the x axis of how much force they are generating, and in the y axis how much is the workspace. Okay. So, our sensible phantom is somewhere over here, desktop phantom, sensible phantom is precision power and 2 thread, yes, there is a sensible phantom. Quanser, yeah, now in Falcon it is over here. These are all over here, sensible phantom. Okay. The little higher version is going to be here, even more little higher version is going to be over here. Okay. So, whereas if you look at the another device called the haptic master, it is going to be over here. It can generate very large force, and the workspace also is very high compared to the other devices. So, most of the devices are over here. Okay. This is admittance type, yes. So, this device, if you look at it, this is the immersion and incorporation. The force range is very less, but it can have a very large workspace. Depending upon the range of the workspace and the force it can generate, the cost also vary. Okay. These are all commercial devices, but there are devices available in the laboratory still. Okay. Again, x axis force versus workspace, if you look at it, there are exoskeletons which can have a large amount of force as well as the workspace. There are in the for example, this device is again like a exoskeleton, but the force it can generate is very less, and its workspace can be very high. Again the problems with the exoskeletons, all these devices can be divided into two categories. One is the ground based, grounded or ungrounded. So, if you look at these devices, it's grounded, it is staying on the ground. So, any force it is generating, it has to be compensated by the reaction force. The reaction force can be transmitted to the ground, whereas the forces you are generating in the exoskeleton, they are all ungrounded. In fact, it is called bodily grounded. So, the generated force has to be compensated by the reaction force on your skin. Okay. So, these are the challenges. If you have a force which is generating on the finger, if you have a small exoskeleton, then whatever the force you are generating, it has to be transmitted over here itself. The reaction force has to be transmitted over here. Okay. So, will that destroy the immersion? Will that destroy the purpose of generating the haptic feedback? That is all the question. These are the challenges now researchers are still facing. So, there are cost wise we can compare it. It can go up to $50,000. Each device can cost about 25 lakhs. Okay. So, Sensible Omni maybe it is about $2,000 or $2,500 as of now. Okay. Now, in Falcon, as I told you, it is $200. Okay. Other vibrotactile devices can be much more simple. Simple vibrotactile device, it can be even $1, but it can develop only the vibrotactile feedback, not the haptic feedback. Okay. So, in all these things, as I told you, actuator is a major issue. So, we are still searching for the ideal actuator. In the whole of the one important challenge in a haptic device, if you ask me, that is the finding the right actuator, ideal actuator. We are still to invent an ideal actuator for the haptic devices. Okay. So, without intrusion, how are we going to generate the force feedback? That is a challenge. Okay. So, we need to find out the position. So, we need to find out the trackers in order to give you the range and resolution and the bandwidth, whichever we have learnt in the human haptics. All those things, without the intrusion, we need to find out the positions. Okay. And then when you are generating the forces and torques, again actuators is going to be a challenge. Again, we know what is the range and resolution and bandwidth of the forces which the human can sense. Can we find out actuator which can match these requirements? Frictionless and backlash. Okay. Backlash in the sense, when you turn front and back, there should not be any change in the there should not be any gap. Okay. If you use gear devices, there is a small gap as a backlash. Okay. So, gears cannot be used in haptic device at all. Okay. If you cannot use a gear, then how are we going to generate force and then transmit the force? So, all those details we will study in the later classes. Again, as we said, mass has to be 0, the inertia has to be 0, that is not possible. Okay. How are we going to overcome all these challenges? Rigorous control of the vibration and then adaptive control, these are the challenges. So, each of these challenges which we are going to see it in the later classes. Okay. As far as the control system is concerned, again for those students who have taken the robotics classes, okay, if you see, you can classify all the control system for robotics into now majorly 4 classifications. One is the motion control, where you can control either the position, velocity or acceleration, or the force control, where we can explicitly control the forces, or the implicitly control the forces. In the explicitly controlled forces, again we can have a open loop or closed loop. In the closed loop we can find out whether the force based explicit force control or motion based explicit force control. Okay, again I will go into the details. Right. Instead of controlling the force, I think most of the robotic control systems are force control based, which is not going to be useful for us. We are going to see that impedance control is what now we need. I think in the human haptics class we talked about why impedance control is necessary. Okay. In the impedance control, again we can have two different types: impedance control without the force feedback, impedance control with force feedback, and then finally a hybrid of any of these things is what you will find it in the robotics. We will be focusing mostly on the impedance force control, and specifically impedance control without the force feedback. Okay. So, all the sensible phantom or most of the devices, they are using this impedance control without the force feedback. So, essentially if you look at the block diagrams for the force feedback, suppose if you have a force controller and let us say this is a target force, and suppose if the controller the robo is giving the force output, the generated force can be compared with this, and then force control can have a output this is the change in the length, yeah, okay, and that is given to the robo. This is a force control with a force feedback, we are controlling the force over here. Another possibility is that position control with a force feedback. Again the output is a force, the input also is as a force, okay, but the position can be sensed and then given to the position controller. The position controller can be given to the robo, but the force also can be given back, sensed, and then add inverse of the impedance. We can multiply it or integrate it to get the okay, inverse of the impedance, and to get the velocity, and velocity if you integrate it we will get a position, and that position is again controlled. So, there is a positive summation over here, and that can be controlled. This is the position control with a force feedback. Impedance control with a force feedback. In the impedance control, what is controlled is the impedance, where the force controller is over here, the force at the output is measured and then summed up over here, the position from the output is measured and given to the impedance controller over here. The impedance control, we are finding the velocity, and then that is multiplied by the impedance. What we get out is the force, and then that force is summed up with the output force or differentiated with the output force, and that is what is controlled over here. Okay. So, in haptic devices we will be using much simpler one, because now measuring the force at the output is going to be extremely difficult. It is going to add a lot of cost to it. So, without the force control, position alone can be used to control the impedance, and that solves the problem. Okay. So, there will not be a force controller, there will not be force measurement, but there will be a position feedback, and then the impedance controller will be there. That is what the usual, for example, the sensible phantoms have been using it. Okay. We will look at different other control systems in the coming classes. Okay. So, as I think I mentioned and why we needed the impedance control in the human haptics class, remember we needed the not only the angle, for example, this is a hypothetical pendulum. If we control the position of the pendulum with the angle control alone, and it will swing back and forth. If we control the pendulum not only with the angle, but also theta dot, then we can control it and then make it not swing beyond this position, and that is what we have. Okay. So, that is the reason we needed the impedance control. Impedance control is the generalization of the stiffness control, which we have seen in the earlier classes. So, this is a simple haptic device which you all are going to make a simple haptic device. Suppose if we have a rod, and this rod is where you are going to hold it, okay, and then you can rotate it. Let us say this is a 1 degree of freedom haptic device. So, the angle can be measured. So, let us say there is a virtual wall over here, and this is a position. Let us say this position is represented by this. This is called the haptic interface point, HIP. So, this haptics interface point, we can check whether it is colliding with a virtual wall at every frame. If it is not colliding, then we do not have to generate a force feedback. If it is colliding, suppose at some time it has come in there, then we need to find out how much force it has to generate. For example, how much torque this motor has to generate in a 1 degree of freedom. So, we will have a different models of force response. For example, simple is it depends upon the depth of penetration. We can find out F is equal to Kx, it is a simplest model, K into, okay, let us say delta x, this is the delta x. So, we know that delta x, let us assume that the virtual wall has some stiffness, and therefore, we can find out the force, and then force can be converted into torque. We can ask the motor to generate the torque. This is a simplest 1 degree of freedom haptic device. We have developed a 1 degree of freedom haptic device in our lab, but having two different loops. One is controlling the position, measuring the position, and another is measuring the velocity. So, in order to render stiffer walls, the virtual walls what you have, there is going to be a maximum limit on the stiffness what you can have as far as the stability is concerned. So, in our earlier work we measured position as well as velocity and then increase the maximum stiffness of a virtual wall that can be rendered by the same haptic device. This is one of our earlier works in 2007. The student who had worked on this is right now working in Apple designing haptic devices. Okay. There are all these devices are for rendering a rigid object, but we can also have deformable objects rendered. We will see the details of deformable objects rendering in a later class.